hexagons. So here are some hexagons. All right. The colors aren't as bright as I might want, but each of these is made by pasting together 6 Pascal's triangles, mod n for various values of n. If you had to guess which of these would correspond to values of n that are prime. Everybody knows what a prime number is, right? Oh, if you had to guess which ones are prime. Actually, 3 of them are prime and 3 of them are not prime.
A, B, and F.
You liked E a minute ago. A, E, and F, you're
A,
saying?
B, and F.
A minute ago, you liked D.
I like that. No, I'm saying A, B, and F I would form as one group and the other, but I don't know which one is prime. They look sort of similar.
Can you go ahead? A is 5. Let's see, you liked A, B, and F.
Totally wrong.
Yeah, B and F are related because one is the divisor of the other. But you can see the ones on the top, the difference is really the patterns are a little crisper. They're, the ones on the bottom have, in some sense, more going on. All right, they have what I like to call competing themes. Okay, go ahead, one more. You can see 8 and 9 are another couple of examples. Oh, shoot, you can't go back. So don't, oh, you can go back. Good, you figured it out. I couldn't figure it out. No, you can go back. Sorry.
No, go forward.
No, forward again. Yeah, there. Stop there. 8 and 9 are more complicated than the ones on the top row, I think, but a little less fraught or whatever than the ones in the middle row. Okay? 8 and 9 are not primes, but what would make me think that 8 and 9 would be different than 6, 10, and 12? They 6, 10, and 12 have relatively prime factors, right? More than one prime factor. Whereas 8 and 9 are a prime to a power. So any of the patterns in 8 and 9 are going to be nested because everything divides itself. Whereas in 6 and 10 and 12, you have these overlapping, competing themes. Okay. And maybe you can see them better with the triangles.
Sorry, how do you say it's nested?
Huh?
The end with 8 and 9 at the bottom?
Yeah.
How do you say it's nested?
It's nested. Sorry, nested. One pattern inside of the other. Go ahead to the next one where I think you can see. You see how there are all these triangles, but they all fit in together. Whereas this has a triangle here and an overlapping triangle here. So this triangle and this triangle overlap. But all of these are nested inside one another. And the same with 9. So you have these things like this sticking out into the other triangles.
And that doesn't happen in 9 and 8?
No, because all of those are divisible by a 9. All of them are 3. So you'd have 3 and then 9, but the 3 would be inside. Whereas if you have 2 and 3, they're going next to each other. So basically you have 3 different kinds of patterns that I'm seeing in this. You have PQ patterns, P to the N patterns, and P patterns. That's the only way I can remember the combination to my lock for when I go swimming, is it goes P, p to the n, and then pq, and I remember which order they're in. But another interesting question, it's not necessarily mathematical, is of these three patterns, which kind of pattern is most aesthetically pleasing? You like crisp and clean things, right? Somebody else might say, I like chaos. I really like the streets of Madras. So here's, I'll take the PQ or whatever. Or I like a little bit of ornamentation, but I don't like things going up against each other, so I'll take p to the n. But then we can go. So that was Pascal's triangle. Now,
If I can ask you, how many rows of Pascal's triangle did you have? Hundreds?
like 125, something like that. I went out longer than that, but like 500 and stuff. But I think the hexagons, I think, were 125. I made these slides a long time ago, so I don't promise that that's right, but that's the order of them. Yeah. So now for some serendipity. When I got back from sabbatical, we had a math hire, and we hired this guy, Mike Barzell, Dr. Mike Barzell. She's one of my students. She just got tenure at Nazareth College a few days ago. I just heard she got tenure at Nazareth. Whoops. Mike borrowed my overheads for his talk. When we have new faculty, the first thing we do is we make them give the talk for our high school math competition. So Mike gave a talk on symmetry, and I had all of these slides from a talk that I had given at a section meeting on this project. And so he borrowed my slides, and then when he was giving them back, he said, have you thought about trying it with non-cyclic groups? Now, remember a few minutes ago when I told you that I did my PhD in applied mathematics? We didn't get to take abstract algebra. So the last time I'd had abstract algebra, I was an undergraduate. So I stopped for a minute and I said, oh, yeah, mod and arithmetic, that is a cyclic group, isn't it? So he worked with me, and we started looking at some other groups. You can take the cyclic groups and basically make ordered pairs of elements and do pairwise addition. And here you get Z2 cross Z2. Now, for these kind of groups, if you're going to generate all of the possible group elements, you have to put one generator down one side. So instead of having 1 down both sides, we have 0, 1 down one side and 1, 0 down the other side. And we get interesting patterns. And then the question that Mike came up with was reflection about the axis down the center of the triangle induces a map from the group to the group. What is special about this map? So this is for Z2 cross Z2.
I'm a bit rusty with cyclic groups.
Yeah.
Can you give a quick primer on cyclic groups?
Okay, a group is a set which has an operation, a binary operation, like addition. Okay, a binary operation takes 2 inputs and returns an output. Now, this binary operation must be closed, so in that if you take 2 things from the group and you do this binary operation, you get another thing in the group. Okay, it has to be associative, so A plus B, do that, and then plus C is the same you get as taking A and then adding it to B plus C. So there has to be an identity, and every element has to have an inverse. Okay? So basically and there are all kinds of things that you study about these groups. And one of the big things that just got done in the 20th century was a complete classification of all the finite simple groups. So,
This map has vertical symmetry.
hmm? This has, there's symmetry, but if you just,
one more comment. Cyclic means that group
Oh, sorry.
can be generated by one element.
Thank
For
you.
example, Z, set of integers, 1 plus 1, take any element, you will get as an addition of 1. So that's a cyclic group.
So the group will be called as a one
If-
specific number.
Yeah.
If it is generated by
Same. If you can
Yeah.
find an element, it generates all.
And basically all the cyclic
So
groups
it is
are,
non-cyclic because Z2 cross Z.
yeah, all the cyclic groups are essentially mod n for some n. You know, you might formulate them a different way, but they're essentially the same. So, but this one's not cyclic because if I started with, say, 0, 1, and I added again, I get 0, 0. If I add it again, I get back here. There's no way I would go from 0, 1 over to 1, 0. So I need two distinct elements to generate this group, which is why we put one down one side and one down the other side, because otherwise we wouldn't see the whole group. Okay? We also look at things like subgroups. If I just look at 0, 0 and 1, 1, that's essentially the same as just having 0 and 1. If I only had those two, I won't get anything but those two. So, and we also have the subgroup, of course, this subgroup and this subgroup. Okay, a subgroup is a subset which is in itself a group using the same operation. Okay? So what is special about this map? This map is an isomorphism. Okay? So we'll come back to that in a minute. So now that we're dealing with groups instead of just regular Pascal's triangle mod n, we put together the names Pascal, and this was Mike's idea too, and Galois, and started calling these triangles Pascalois triangles. And you can construct a Pascalois triangle by first associating with every element in a finite group a different color, then placing one element down one side of the triangle and a possibly different element down the other side of the triangle, and use the group operation to generate the colors for the rest of the triangle, the interior. Okay? So Pascal's triangle mod n for any integer is one kind of example of Pascalois triangles. Okay, but they're not the only one. So, back to the question. We have a theorem. It's a math talk, so you got to have a theorem, right? In Pascalois triangles generated by, Zn. Zn is the notation used to represent the cyclic group with n elements. Cross Zm, where 0, 1 is placed down the left and 1, 0 is placed down the right. Reflection about the central vertical axis induces the automorphism. It's not just an isomorphism, it's an automorphism, given by Rs goes to Sr, if and only if n equals m. If n doesn't equal m, then reflection across the thing doesn't even induce a set map. And you can see this over here with Z3 cross Z2. If I look at, let's look here, blue needs to go to green, right? But up here, blue would go to, right? They don't always go to the same colors. It does not happen here. If you see this, take any color, this green goes to that purple. This green goes to that purple. Always goes to the same thing. And if you want a proof, you can see the Pascal Triangle, a tool for visualizing abstract algebra in the Innovations in Teaching Abstract Algebra MAA volume. Okay? So here are some other examples. All right, and now I'm telling you how many rows I have. So you can see the kinds of patterns. So another thing that we see is, well, actually, never mind. I'm going to say that later. The next question is, how about non-abelian groups? Okay, the thing about the operations that we've looked at so far, they've all been what's known as commutative. A plus B is the same as B plus A. Okay? But there are groups that have a binary operation where the operation is associative, but it's not commutative. So AB and BA are different things. And those groups are called non-abelian groups. And go ahead. An example of those would be D4, the symmetry group of a square. If you look at all the possible ways you can move a square so that it looks the same, you can rotate it by 90, 180, 300, and, well, 270, and then 360, or you can reflect it about, you can flip it on the, so